Okay, in general, ignore the stuff in orange for the moment. If you have an m by n matrix A, you can define the matrix T of V equals AV. And that matrix will go from Rn to Rm. It starts in Rn because an m by n matrix has n numbers in each row, and you have to multiply it then by a column of n numbers to make any sense of it. So we have to start with the vector v in Rn and map that to Rm because, of course, there are m rows in this matrix. So, I'm just looking to see, yeah, I can see that, okay. Because each row gives you a number in the column vector that you get over here. Now, as usual, you have your row space of A and your null space of A. And over here, you have your row space of A transpose, which is the column space of A, and the null space of A transpose. We also note that the row space of A is orthogonal to the null space of A, and it's the same over here. The row space of A transpose and the row space of, or the null space of A transpose are orthogonal. Not only are these orthogonal, but any vector in Rn can be written uniquely as V equals V row plus Vn, where V row is a member of the row space, Vn is a member of the null space. Now that is very, if the row space was represented by this axis and the null space by this axis, or vice versa, let's make that the null space and this the row space, then any vector out here, if this was, if these spaces were in R2, any vector in R2 would be a sum of unique vectors here and here, one parallel to the row space, one parallel to the null space, or one in the row space and one in the null space. Okay, so this vector plus this vector could be expressed in the head to tail picture this way. So this vector is this. So this would be like your V row, and this would be like your Vn, and this would be your vector V equals V row plus Vn. Not only equals, but equals uniquely. Put that exclamation part over the equal sign because there is only one V row and one Vn that add up to this vector. And that's very clear if you understand just R2. And it's very clear how that extends into higher dimensions. So that if I have the vector V, again, here's row and here's n, projecting V parallel to n gives me this V row. Okay? Now, if you think of the row space as a plane and V as a vector that's out of the plane, you just project that vector down perpendicular to the plane or parallel to the perpendicular or the orthogonal space n of A, and you get something like this. An orthogonal projection here, and this will be your V row. And of course, this dotted line, if you fill it in with a vector, becomes your Vn. Okay, so these are important pictures, but you do have to understand in terms of these pictures that you could be dealing, already up here, if we look over in our six-dimensional space that we get from our 6 data points, from trying to model our 6 data points, at least one of these things has dimension greater than 3. We can't even sketch it. We can't even sketch a representation of it because all we can visualize is 3 dimensions. you know, this might be a 6-dimensional space, and your null space might be a 2-dimensional, well, this might be a 4-dimensional space, and your null space a 2-dimensional space. You know, if we think of these two spaces. Now over here, you know, our model, we're just in R3, but we could also be doing models in much higher dimensional spaces. In a 50-dimensional space, this might represent a 30-dimensional space, and your, or this axis might actually represent a 30-dimensional space, and this axis might represent a 20-dimensional space. So don't take these pictures literally about planes and lines, but this does illustrate the relationships among V and Vn and V row. Okay. And then we say that V row is the projection of V on the row space, projecting parallel to the null space. Now just plain old vectors, 2-dimensional vectors, the situation might look like this. Okay, well, let's now come back and start being a little more specific to the 3 by 6 matrix that we're dealing with.